Before I start, I want to comment that you are welcome to try to solve the questions in the homeworks by discussions. So you only need to. So the only requirement for you is to, in the end, when you write this up, you have to finish by independently. So you are welcome to discuss how to solve the problems, like and. This is actually, I think, is the best way to learn. So instead, so if you are really smart, if you think you can finish them independently, then you are welcome to do so. But if you are stuck, then please try to find other classmates and discuss with them. And you can even discuss with TAs to ask the TA to how to proceed for this specific homework problem. And please let me know if you have any questions regarding the midterms, and if you have any questions for the future finals, you can also ask me. The finals will cover the chapter up to chapter 7, so it's the chapter after today's chapter 6. The last chapter will be about the electrodynamics. And you actually have already learned quite a bit electrodynamics in the physics 2041 already. So before the next lecture, please try to review what you have learned in physics 2041, especially the chapter 9. So a lot of what you're going to learn in chapter 7 will be based on what you have learned in 2041. And so try to refresh your mind. So last lecture we discussed the bound current. So from the bound current we can define the from this magnetization vector we can find out the bound current distribution, and then from this bound current distribution we can define auxiliary field that is simply called the H field. So even though it's a magnetic field, it doesn't have a specific name. And then in the very end of the last lecture, we discussed the boundary conditions for this H field. So we from this by applying a Gaussian surface, we can determine the field in the perpendicular direction. And by using an Amperian loop, we can determine the field in the parallel direction. And now we have 4 different kind of boundary. We have 2 sets of boundary conditions. 2 is about the H field, and another 2 is about the B field. So to visualize that, we plotted what the B and the H field should be for a permanently polarized material. Permanently magnetized material. So it's like a bar magnet. So for a bar magnet, the magnetization vector simply points from here, say the North Pole and the South Pole, so point from one pole to the other. And last time we already showed that the H field should be in the negative direction of the M field, because typically this magnetization vector contribution is larger than the B field inside the material, and it's also a negative sign. So inside of the material, the B and the H flip side. And but we haven't talked about what actually happens in the boundary. So the boundary condition here is, let me copy this to here. So now let's take a look at the boundary conditions. So for the H field, here in this problem, there is no free current. So here the Kf is always equal to 0. And that means that this H parallel should always be 0. And in this H perpendicular is actually different, is the difference between the magnetization vector between the two edges in the parallel direction. So keep that in mind. Now we have two different kind of edges. One is the edge over here. So along this edge, the magnetization vector is parallel to this M. So you should, then in that case, this quantity should be 0, right? Because this is calculating the perpendicular direction of the difference of M. And inside, the perpendicular direction of M is 0. And outside, the perpendicular direction of the M is also 0, because this M is along the perpendicular parallel direction of this edge. So this means that the H field should be continuous along this the edge over here. So as you can see now, the plots here show that the H field actually points from here, and in the center it goes straight to the left, but here it goes slightly upwards and until it smoothly crosses the edge. So the H field is always smooth at the edge over here. So it almost looks like a problem where you can think of this being some surface magnetic charge and at the North Pole. So you can think of this as magnetic charge North Pole here and the magnetic charge South Pole over here. Then this is extremely like a parallel plate capacitor. So in the when it's when it's inside this parallel plate capacitor, it's almost parallel to this two plate direction, and this field is simply the fringe field. Okay. Oh, so the surface that I'm right now interested in is the red one here. So it's you can think of this as a three-dimensional cylinder, and the surface, or you can think of this as this rectangle. So it's a cube of a cubic bar magnet. So right now we are looking at the surface over here. So on the side. So the surface vector n is here in this direction, and so above, and so the m vector should be in this direction. So the m vector is perpendicular to the surface direction. So this m perpendicular is 0. Is that clear? Any other questions? Okay. So, so here in this problem, the because the perpendicular direction is 0, right? And then here the free current is also 0. So the edge should be smooth everywhere except that there are some place that has this jump. So this jump is actually something that we analyzed before. So in this bar magnet, this jump is this del dot m, right? So the del dot m is non-zero at these two edges. So we can if we so it's almost like a electric static problem. And if we assign this is the north pole as a plus charge, the south pole as a minus charge, then the H field is very similar to this E field. So now let's take a look at the B field. So for the B field, oh sorry, we haven't actually gone through this edge yet. So at this edge, you have to be careful that even though the K free is 0, there is this term here. So the H field near the edge over here is discontinuous. So as you can see that the edge here is pointing towards to the left direction, while over here is pointing towards to the right direction. So this discontinuity is given by this M perpendicular. Now let's go back to the magnetic field. So for the magnetic field, the perpendicular direction is always 0, and however, the parallel direction, the K free changed to K. Well, we have already learned that for a solenoid, there is a if we consider a cylinder, then there is a surface current flowing along this side. So let me see. So for this surface current, it contributes to K, and then this K cross N. So the N is pointing out of the cylinder. So the K cross N will be something that's finite and near this edge. So you would imagine that this term is non-zero. So now if we check this plot here, so this for this magnetic field, this for the inside in the perpendicular direction, the change is zero. Let me see. So if you project, say, the field line over here to the perpendicular direction, then there is something pointing into this surface. And then if you project the field line over here to the perpendicular direction, it's also pointing downwards. So this perpendicular direction is the same, but apparently you can see that in the parallel direction, one is pointing to the left, one is pointing to the right. So the parallel direction is of opposite direction, and that's because it's non-zero. Okay, so we will actually talk about this later. That it's you can mathematically you can indeed rewrite this problem into a magnetic north pole sitting at over here, and a magnetic south pole sitting at here. So this mapping to this electric static problem is actually true, mathematically speaking. So even though there is no such thing as magnetic monopole charge, but to solve this problem, it's actually indeed helpful and intuitive for us to compare that with the electrostatic problem. So before we do that, let's go through the final two things that's in this chapter. So the first thing is the idea about the linear media. So previously we haven't talked about how the magnetization vector M is being produced. So it can be a linear media that produces this magnetization vector M, or it can be a permanently magnetized object like a ferromagnet. So here, first I want to discuss the linear media. Just like the polarization vector is linear in terms of electric field, here M vector magnetization can also be linear in terms of the magnetic field B. But because of some historical reasons, typically in magnetic field, in magnetostatic problems, we actually don't write the M in terms of B, but using M in terms of H. So the auxiliary field H, which simply calls the H field. So the reason we do this is because here this H field can be actually measured easily, because this H can be directly produced by this free current. So in experiments, we typically apply a current to a loop of wire and then produce the H field. So the H field is easy to know for experimentalists than this B field, where in the electrical static problem, we typically can measure the electrical field E, and the D field might not be easy to measure. So that's why the P is typically written in terms of E, and the M here is typically written in terms of H. So now, aside from this subtle difference from this electric static problem, everything else follows. So we also define the magnetic susceptibility instead of electric susceptibility. And this another thing that you want to be careful is that here M has the same unit as the H, where this P doesn't have exactly the same unit as E. So when you are doing a mapping between a magnetostatic problem and electric static problem, you have to pay attention to the units of these quantities. So this chi M is a dimensionless quantity, and different from this electric static problem, the chi M here can either be positive or be negative, because for positive, the M is along the same direction as the magnetic field, and it's a paramagnetic. And when chi M is negative, then it's a diamagnetic. Where in electrical fields, this chi E is typically a positive number, but also small. So here, this chi M is typically a small number, so on the order of 10 to the minus 5, except for some special materials. And for all this material that obey the equation over here is defined as a linear media. So pay attention that here this linear also implies that it's isotropic. Now, if you write out the B field, then the B field is equal to the mu naught times H plus M. And now if we rewrite this M in terms of H, we get the chi M here. And this 1 plus chi M is simply similar to the quantity that we see in electrostatic problem. We can define this entire thing as the permeability of the material. And in electrostatic problem, the corresponding quantity is permittivity. So try to pay attention to the subtle difference. So in the vacuum, this chi M is 0, and the permeability is simply the mu naught, and that's called the permeability of free space. I guess you are already familiar with all this in the physics 2041 already, right? Okay, so any questions? Okay, now let's try to discuss a bit more about the parallelism between the electric field and the magnetic field. So now I want to emphasize that this is simply a mathematical tool, and that's valid only under special conditions. So not everything that we discuss here can be mapped from the electric static to a magnetostatic problem. So the very important condition is that if in the problems there are no free charge and no free current, then the two can be mapped to each other. So consider the case of permanently polarized material, whether it being a polarized or a magnetized object, the two problems can actually be mapped to each other. So the reason why it can be mapped is because mathematically speaking, they obey the same set of equations. So now, if we take a look at the electrical static problem, I hope you still remember that first this del dot D equals 0. So do you know the reason why del dot D is 0 here? Yes. So in principle, the del dot D should be equal to the free charge, rho free, right? So here, this equation is correct because of no free charge. And del cross E is 0. That's because the Maxwell's equation dictates that the curl of E must be 0. And then the final equation is simply the relation that relates the E, D, and the P vector. And now let's go to the magnetostatic problem. So the del dot B is the condition implied by the Maxwell's equation. And the delta dot cross H equals 0. That's because the problem we consider also has no free current. So this is not always true. And so only in this special case where no free current exists, then we can have this condition. And the last one is simply the definition of this relationship between HB and M. Now, if we list these two sets of equations, then we immediately can see that the del dot and del cross terms equations are identical, and the third equation can also be identical if we do a simple mapping. So here, the first equation says that we simply need to replace D by B, right? And the second is simply replace E by this H. And then in the now if we do this replacement, so D becomes so B and D are equivalent, and then this E and H are also equivalent. So now what we need to do is to do the replacement here, that if we replace the final epsilon naught by this mu naught, so the epsilon naught must be replaced by mu naught, and then replace the p by this mu naught m. Then if we do this replacement, the third equation also identical to each other. So then this means that now we successfully mapped electrical static problem to a magnetostatic problem under these two equation conditions, and this actually maps a lot of problems from the electrostatic to the magnetostatic. So for example, this is a question actually from homework that I'll discuss here. So this is the question 6 from the homework 5 that we are going to finish soon, next Thursday. So in this homework, you are supposed to find out the magnetic field of a uniformly magnetized sphere. So but this problem we've already done a similar problem that's uniformly polarized sphere during the lecture when we are studying the electrical static problems. And the solution that we find that inside the polarized sphere, the electric field is minus 1/3 epsilon naught times the polarization vector p. So now what you want to do is simply to look at this expression and change the symbols. So then this means that here use the relation over here. You simply replace the E by H and P here by the mu naught and the epsilon naught by this mu naught. So we immediately see that this H must be minus 1/3 mu naught here, because mu naught, epsilon naught is changed to mu naught, and the P changed to mu naught m. And then this is the relationship between H and M. And we also have in the end the relationship between H and B and M, right? And since we already know the H field, then we simply use this equation over here and immediately write out the B field. So if you want to compare, you can also find out the surface current induced by this uniformly polarized magnet. That's something that we actually have done in the previous lecture. You can try to compare your answers to the simple trick here to see if they agree with each other. Okay, so Next exercise that I want to discuss is the finding out the magnetic field over a sphere due to the steady current within that sphere. So for this problem, we have also finished the calculation in homework 2 question. The last question, maybe it's question 6 or 4. I don't exactly recall, but if you still remember, it's a 4-step process that you need to do the derivation, and the final result should be for the average the electric field. So now we map to this electric field over a sphere due to the charge or polarization. So the final answer in the homework 2 is that the average electric field should be minus 1 over 4 pi epsilon naught P over R Q. So I don't know if you still remember what you have done in the homework, but that is what you have proved in homework 2. And now in here we can even generalize the conclusion from this electric static problem to the magnetic static problem. So here we simply need to recognize that the P is simply the total polarization vector over this entire sphere, and then this we see that there is a relationship between the E average and the polarization vector P. So now the next step is simply to replace this P by mu naught m and the epsilon naught by mu naught. So and what's on the left hand side should be E replaced by H. So here this is H average, and the mu naught here cancels. So what's left over is simply and the integration of the magnetization vector m total is simply the little m, which is the total magnetic moment m, total magnetic dipole moment. Sorry. Now from this m average, we can then next determine this B average, because the M average and the B average are H average are related by this M vector, because here B field is mu naught times H plus M. So this B average should be this H average, which we plug in here. So it's and plus the mu naught m average. And this m average is simply the total m divided by the volume. So it's 3/4 pi r cubed. Now if we combine these two terms, we can write down the final answer as here you can see that this 3 goes above, and one of them cancels with the left hand side, so there's a factor of 2 coming here. So you see that there is actually a subtle difference in the answers. So here in the previous electric static problem, the factor is -1, and here in the magnetostatic problem, the factor is +2. So if you go back to the lectures, you can actually also note this difference of factor. So, any questions? Oh, you mean the m vector? Okay, yeah, thank you. Okay, so I hope this will help you solve the question 6. And next, I will also discuss some of these homework problems. So this is for homework 4, I guess. So it's either homework 4 or homework 5. So it's one of these optional questions, but I'll just go over some of the techniques here. So the idea here is also similar to what we just discussed. So we want to map the electrostatic problem, the skill that we have learned in the electrostatic problem into this magnetostatic problems. So again, the condition here is the same. So under the condition where there is no free current, then the del cross H is exactly 0. So when this del cross H is 0, we know that H must be able to be written down as the scalar potential. So here this scalar potential is only works in these special conditions and not works every time. So we denote this scalar potential as the capital W. So now if we make this definition of the scalar potential W, then if we apply this Laplace vector, we can see that the del square of W can be written down as del dot H, where for the del dot H is related to the H are supposed to be written down as the sum over B field and the M field, but we know that the del dot B is always 0, so the H can only be written down as a single term of M. So just as we discussed, that the H is in the negative direction of this M, because it's here the H is B over mu naught minus M. So then now if we translate to the right hand side, it should be del dot M vector. So now I don't know if you recognize that here this del dot m is actually something that's called the source term. So that is what we imagine as the magnetic monopole. So now if we go back to here, the del dot m is similar to the del dot p, right? So this del dot m is non-zero at the edge over here and the edge over here. So that's why that this this magnetic static problem is so similar to this electrical static problem, because mathematically speaking, because in these problems there are no free current, then indeed there is a mathematically valid scalar potential, and this scalar potential has a corresponding source term. So the source term is del dot m, and this source is actually similar to this to the free charge in the electrical static problem. So that's the mathematical meaning of magnetic monopole. So if you have to remember that this is not physical, and in reality, this problem is produced by the surface current running over the sides, and this magnetic monopole is only a mathematical tool for you to easily solve the problem. Because now if we mapped this to a plus charge and the minus charge here, then we can actually use what we have already learned in this electrical static problem to solve this problem. So this is similar to a finite size parallel place capacitor. And indeed, that's why the field here looks so familiar to you, that this is the field inside, and this is simply the fringe field. Okay, so we will take a break here and finish this problem later.